Hello, everyone, and thank you for joining us today for our Quantum Speaker webinar series. This is hosted by ATARC's Global Quantum Working Group. I'm Lily Chen, one of the group's government co-chairs. We are very excited to welcome Dr. Venkatesh Kannan to speak with us today. At iCheck, Venkatesh is responsible for the strategy, implementation, and the partnership for R&D into the technological solutions to develop and the use of the HPC and the data platform by national and EU users across academic research, enterprise, and public sector organizations. There will be time for questions at the end of the presentation. Please feel free to use Q&A feature or raise your hand and you will have an opportunity to speak. Welcome, Dr. Kannan, please.
Thank you very much, Lily, for the introduction, and hello, everyone, for joining today. So as you might have already received by email, I wanted to basically bring to you some thoughts on the considerations, the motivation, and the opportunities that as a high-performance computing center, we face when looking at one of the emerging computational paradigms in the quantum computing and the simulation world. So my name is Venkatesh. I work at the Irish Center for High-End Computing as the Associate Director for Solutions R&D. And if you're already familiar or if you're new to this, high-performance computing centers, HPC centers, are present in many states to provide access to computation and in some cases computational data storage for academic, enterprise, and public sector use, focusing on research and innovation activities at national and regional levels. So the focus from our point of view in providing these platform services is to support research, development, and innovation across different sectors. And more often than before, we are seeing a strong convergence across academic researchers, those in enterprises and public sector coming together and working on challenge or solution-based problems. So in that sense, the next 20 odd minutes, I would like to spend on sharing over the last 3-5 years, what has been the motivation and limitations for us HPC centers to look at this famous quantum computation and simulation paradigm with different kind of presentations of its opportunities, capabilities, and limitations. So to that effect, what I would suggest is please look at this from the perspective of not commercial use of these resources and services, but more for research and innovation. So the primary motivation has been in the last decade or so, the realization of experimental quantum computing and simulation devices in hardware has emerged to kind of stabilize so that these experimental devices are now accessible not just by its developers, but some expert user communities that know how to define the problem in this paradigm, program these devices, and get some results out of them, irrespective of their limitations at this stage. So the experimental access to these devices has already been seen in multiple iterations in the past. 12-15 years ago, when GPUs were open for the wider programming community beyond the visualization community, we as HPC centers and also the scientific and enterprise user communities adopted them for more mainstream computational applications as well. So as HPC centers, we had to embed general purpose GPUs more as Oh, my apologies. I just realized probably I'm not sharing my screen. So I hope you can see the screen now, in which case you've not missed too much in terms of the slides. But the motivation on providing access has been to make available these computational devices for different parallel programming paradigms. And 12 years ago, we increased the portion of the HPC infrastructure that provided access to these general purpose GPU devices. Now, at this stage, we are looking at quantum computing as one of the emerging paradigms that seems to be requested by our user community, but also is gaining experimental access from the developer community. So in that sense, we believe that it's worth looking at the maturity of the quantum computing paradigm, the kind of skills and problems that are more suitable to this computational paradigm, and what it takes us as a HPC center to make access available to these and support our users in terms of skills, in terms of the tooling, in terms of the skills development program that we need to share with our user community. Now, the use of quantum computers in the context of HPC, it depends on what the problem space is. The more advertised use case for quantum computational devices in the world of high-performance computing has been as potential accelerators, so to speak, that they can solve problems that are potentially intractable in future when their current limitations are overcome. So in a broader sense, quantum computational devices are seen as yet another type of parallel programming or parallel problem solving device in the world of high performance computing with more precision, accuracy at more scale, etc. Now, the other way around is also an equally valid use case whereby high performance computing, the classical HPC, serves the quantum computational community in terms of not just emulation of quantum systems on classical HPC, but also for the control of these quantum computational systems on compilation of the problems into a standard that is mappable to the quantum computation device. They are all highly computationally intensive problems. So HPC devices can also serve to use the quantum computation device for control and compilation and error modeling. So that is primarily the motivation why the HPC world has been looking at the quantum computation world. Now, more specifically, what are the potential benefits at this early stage of the quantum computing technology of interfacing them with the HPC world? In the longer run, it's potentially to solve specific parts of a computational problem that are more suitable for the quantum world as an offloading from a more hybrid workflow. But in the shorter and medium term, the primary benefit for the quantum computing world is that we can leverage all of the established mechanisms, resources, and skills from the classical HPC world on how to provide access to these quantum computing devices, how to potentially operate them, and how to expand the user community of these quantum computing devices, because there's a heavy co-design exercise that is important in building more scalable and resilient quantum computing devices. I'll come to that in a moment. But this integrated development approach allows for a co-design of a hybrid use case or a hybrid problem composed of classical HPC and quantum computational parts to inform the development of the devices, and vice versa for a more hybrid programming environment to enable more hybrid use cases being addressable going forward. And all this leads to is that it's necessary to have a portfolio of tools and practices that allows a seamless compilation of these hybrid problems, of optimizing and mapping different steps of these problems to devices that are deployed, and also to look at how to execute and orchestrate the hybrid application on hybrid platforms, and also benchmark and evaluate their performance compared to the more classical solutions that we have at this stage. And it's important that we start exploring what is a valid hybrid use case or an application from a HPC quantum world, and not just build a device that potentially does not have an application. So it's important to start from, are there suitable problems that demand these kind of hybrid resources being built going forward? So in that spirit, this is not a slide that is meant to be exhaustive, but it's just a few collection of examples around the world where HPC centers and organizations are prototyping these hybrid platforms going forward. So closer to home, the middle one on the top row is the European ecosystem. So the quantum flagship program in the European Union drives the development of quantum computational devices and technologies at large. The Euro HPC joint undertaking is a European instrument that deploys these quantum computing technologies in different environments, in different HPC environments. So some of the prominent projects you might see publicly available now are the HPC QS that is deploying two Rydberg atom-based quantum simulator devices in two sites across Europe, and a partnership of 16 member states, including Ireland, is co-developing the hybrid platform from hardware to applications. And the Euro QCS is a program that is scaling that initial approach. As a part of the Euro QCS, there are 6 other additional activities that are starting later this year that deploy different experimental modalities of quantum computing devices across 6 different sites. So between the HPC QS and Euro QCS, the Euro HPC joint undertaking is developing a constellation of hybrid HPC quantum computational platforms for access to the community across Europe, primarily for research and innovation access to academia, industry, and public sector. But alongside that, there are also regional activities like the one in the Leibniz Supercomputing Center in the Munich Quantum Valley, which is a regional activity in Germany. In Australia, the POSI Center is also been deploying diamond-based quantum computing devices, and across the US, the Oak Ridge and Los Alamos Lab have similar activities, and also there are other regional activities in Japan and the Nordic Alliance in Europe, etc. And this is just growing going forward. Now, this very much complements what entities like the Amazon Web Services are doing in providing access to an array of quantum computational technologies through their cloud services. So this very much complements that commercial entity. Now, the European activity is all meant to be free for access for the European research community. The different approaches taken by, at least within Europe, in interfacing HPC and quantum computing systems are very varied. When I mean varied, it means you could deploy quantum computational devices which come in the form factor of blades and racks within a HPC cluster, where the QPU nodes, so to speak, have lower latency to the classical processing unit nodes. You could also, there are also activities that are deploying a medium to high latency devices within a data center, whereby optical connection is established between the HPC cluster with access to quantum computational devices elsewhere within the same data center. So we're looking at a latency model where the latency is slightly higher to medium range. And then there are also mechanisms whereby there is a federation of classical HPC and quantum computational systems that are linked by fiber optical cables across a regional network. So you have a spectrum of latency models with which quantum and HPC devices are being interfaced. And as a result, the way in which you provide access to these devices between themselves, the way in which you allocate resources, the way in which you program you have the programming model, the way in which you have your software libraries to account for the latencies and the shipping of different data and control mechanisms to these devices, and also the applications, the type of applications that you can build on these different latency models changes. So it's almost a portfolio of applications that you could look at from these different ways of interfacing HPC and quantum systems. Now, the challenge is primarily when we are doing this interface exercise the ground is shifting our feet as we do it. But broadly speaking, the challenges start, if you look at from the lower part of the stack in terms of infrastructure to the higher part in terms of applications and skills. The challenges start from how do you deploy and interconnect and operate these experimental quantum devices, which are very finicky, so to speak. The qubits are very much prone to the environment in which they function. How do these experimental devices, how can they be deployed and operated in these more beastie operational HPC environments, which are pretty loud, they're quite warm, they are at scale, their operational reliance is much higher. So how do HPC centers, physically speaking, the data centers have to be prepared to operate some of these quantum computational devices on location? How do the HPC centers people, in terms of systems administrators, data center operators, in terms of platform engineers, how do they embed the access to these devices as a part of an operational service? What is guaranteeable, what is not? How do you embed maintenance cycles that are required for these quantum computational devices alongside operational HPC environments? You just cannot probably let a quantum computational device provider walk into a data center without feeding all of that requirements into the operational mechanism. Then as we go further up the stack, the quantum computational ecosystem has been almost growing in isolation in terms of the system software programming environments, the programming libraries, the programming languages. All of that is pretty much mostly Python based because it was easier to build things and provide access to the more traditional data scientists world. There are still programming frameworks which are still based on the classical HPC-like languages in terms of C, C++, not yet Fortran, but still the development of the programming environment for the quantum computational devices has almost developed in isolation of the classical HPC world. But now there's a good opportunity. It's almost timely to have more synergy between the system software, the programming tools, and the workflow orchestration environments. And as I mentioned, all of this has to be informed by valid identification of hybrid use cases. Now, some of the hybrid use cases, like the VQE or the QAOA or parameterized quantum circuits, they do not necessarily by default need heavy HPC systems, but once you start getting into certain optimization mechanisms in variational variation algorithmics, once you start getting into compiling more complex quantum circuits, then the classical parts get more computationally intensive. So it's important to identify within a genuine computational workflow that requires computational complexity, which parts are required, which parts genuinely demand a quantum computational paradigm for that. And last but not least, at this stage of maturity of the technology and its integration, the teams that work on quantum computation applications and algorithms, but also the hybrid HPC quantum, are multidisciplinary. And in many cases, we are composed of teams which do not speak the same language from a scientific or technical point of view. We are speaking about people that are well-versed in quantum mechanics, information processing, and physics-based systems for computational chemistry or optimization systems. And then there are people that are more HPC-based in terms of systems administration, in terms of software engineering, software development, and etc. And then there are people which have the use case ownership or the application or the application domains experts. So we're talking about three different almost categories of people learning how to speak to each other, define the problems, break it down into approaches, algorithms, implementation, and giving the results back for interpretation. Because many of the problem spaces are deterministic in the classical world, whereas by default, the quantum programming environment itself is probabilistic. So how to communicate and interpret the results across these different communities is also a learning exercise. So it's about building interdisciplinary skills to leverage quantum computing within the classical world. So to address all of these challenges, I wouldn't explain all of this in detail, but broadly speaking, we identified across these global centers that are looking at deploying HPC and quantum computing devices. We realized the challenges are across how do you couple at a full stack approach the devices? How do you define benchmarking and evaluation mechanisms between hardware, system software, and applications? How do you look at developing the skills and a competent workforce? Even it's about training the trainers, because we are looking at a new set of people that can deliver these training and education programs. And how do you define a roadmap to, on one hand, watch how the quantum technologies landscape is evolving, how these devices are maturing, what are the continuing challenges, what technologies are evolving, but how do you still continue to synergize the classical HPC and the quantum computing world? So it's almost about creating a phased roadmap. So out of this was born the IEEE Quantum HPC Working Group. Now this is hosted within the IEEE Quantum Initiative. But this was basically a few HPC centers coming together over the last 2-3 years with the same set of problems. And we realized on one hand, while HPC and quantum is evolving independent of each other almost, the HPC centers and quantum computational device providers are also almost working on bespoke solutions in interfacing them. So what we realized was we needed a mechanism whereby we bring the community together, have the community share the best practices or the lessons that we are learning at the moment, and how do you implement a more sustainable and structured discussion and sharing of expertise and resources that are being developed at a global level, because it's only a very small group at the end of the day. So how do you look at enabling the definition and development of the solutions, and how do you unify or not standardize yet, but look at a community-driven definition of different methods by which you can integrate these solutions and applications. So the working group now, the key stakeholders that we bring to the table are representatives from the HPC centers. We're also looking at the quantum computational technology developers, the developers and operators of the HPC systems and software, and also the applications and end user communities. Now, the structure of the working group itself looks at these 5 pillars or spokes, so to speak. They're not mutually exclusive, but they are tied together. The 5 spokes are looking at the identifying the hybrid use cases, identifying how and what kind of system software tools and programming extensions are required, what it takes in terms of software, but also policies and practices to manage the hybrid infrastructure, how to provide access and provision these systems for the users, and how to define skills and development programs. So I realize there are 7 minutes remaining. So what I'll do is I'll just say that for each of these spokes within the working group, we are building a special interest group. And what that means is people from the stakeholder community that I mentioned across enterprises, academic research, and public sector. We are building a core set of teams across these spokes with co-leads for each spoke to basically define what are the current problems, what are the use cases or opportunities, and what are some of the current practices that can be shared across the community. So depending on what your background is from, you may resonate with one or more of these spokes, and you may be interested in engaging in the discussions and contributing to the building this knowledge base. Now, without going into the details, I'll be happy to share these slides if you're interested. But at the end of the day, who's been working along with myself? So the Leibniz Supercomputing Center, TU Munich, the Los Alamos Lab, and the Oak Ridge Lab. So the 5 of us have been establishing this Quantum HPC working group. You can read more about it from within the Quantum IEEE webpage under the working groups. Feel free to write to this distribution list. We officially launched this at the IEEE Quantum Week last year. And we have been having regular sessions at the IEEE Quantum Week in the US, at the supercomputing in the US, and also the international supercomputing that happens in Germany on an annual basis. So feel free to refer to the program and write to us if you're interested. So with that, I'll probably give back 5 minutes to take any questions if you have.
Thank you very much. And we have some questions in Q&A. So let me ask if someone wanted to just ask, because some post 3 pieces. So David Liu, would you like to ask, combine your 3 questions? Or you want me to say the first question?
Read David's. Sorry, Lily, I can read David's questions as well, so I can make a first pass at that.
Okay.
David, I see your probably your latest question on the HPC QC.org. So as you might already see, there's an overlap between the Munich Valley, the Danish partners there, and this one. So they're not meant to duplicate each other. Rather, the birth of the HPC QC ORG was out of a strategic collaboration between the Munich region and the Danish activities. So they are definitely an activity with whom this working group engages. So I would see that we work in synergy rather than in isolation of each other. In terms of the Euro HPC JU program, of course, you can find public information at the Euro HPC JU program, but I'll also be able to provide some links or references to these or the JU activities if we can share them with the attendees after this meeting. And I see your other question, it's quantum computer program. I'm not sure if I get that question correctly.
Then about the copy of slides, that's the next question. I think we will post the this record together with the presentation. Is that correct, Amy?
Yes, that is correct. So we will be posting this recorded webinar on ATARC's YouTube channel.
So the next question is from Allison. Are you going to ask her or you?
Sure, I'm happy to ask the question. So I had two questions for you. One is on the EU programs are explicitly inclusive of the different quantum computing modalities. You have annealing and gate, and you mentioned hybrid. Wondering how your program in Ireland and the IEEE quantum program is looking at engaging with the variety of different modalities. And the second question was on workforce development. In Canada, there's actually programs where, like the Quantum Algorithms Institute is working with quantum companies in order to help train folks up on algorithm development. And so wondering how you are tackling workforce development and working with private companies.
Sure, thanks, Alison. Thanks for pointing out the Canadian link there as well. I'll be interested to read more about it. So I'll take your first two questions in two parts. So in terms of the EU activities, the modalities where it started with the pilot HPC QS, where there was a call for a Hamiltonian time evolution based device to be deployed. So that was called for in 2020, and a 4-year project started in 2021. So as a result of that, that's where I mentioned the neutral atom-based devices were deployed. Now, the 6 follow-on activities that I mentioned for multiple modalities, they were specific that because the joint undertaking wanted to provide access to superconducting-based, ion trap-based, neutral atom-based, photonics-based, etc. So the 6 different activities deploy 6 different gate-based models now. Now, there is also a current call, a third call open from the joint undertaking for further devices. Now, we may not have more modalities, we'll soon run out of them, but I believe at least there are different developers of these modalities that are targeted for deployment. So that's where now the annealing-based solutions have not been called for yet, but there are regional activities and institutional activities that have deployed, for example, D-Wave technologies or other digital and analog annealing-based technologies out of their own activities. So these are being pooled together in a catalog of resources to access at a European level. At a national level within Ireland, we are a partner in the HPC QS and also the Euro QCS projects. So while we are not procuring the devices ourselves within Ireland for the moment, we are co-developing the deployment and the integration stack, so to speak, of the software and applications with the remaining partners that are deploying these devices. So we are working with those that are purchasing or procuring these devices and developing the full stack integration with them. Now, in terms of the workforce competence development, now it has thus far been embedded as a part of the existing HPC QS and Euro QCS projects. Now, that's not ideal, but there are work packages, so to speak, that address skills development and training material being built. But an explicit call is now open. It closes on the 14th of May this year. It calls for establishment from the joint undertaking, the Euro HPC joint undertaking, the establishment of 2 quantum centers of excellence. So they are meant pretty much to build the competence and support the community in terms of skills and knowledge transfer, as well as developing algorithms and applications for specific areas of priority for the first iteration of the centers of excellence. Now, these are based on the existing HPC centers of excellence that have been running for the past 8-9 years already. So we expect these quantum computational centers of excellence will evolve into the future as well.
Thank you for the talk, and thank you for all the questions. We probably couldn't have time to finish all the questions, and but I'd like to thank everyone who has asked the question, and specifically thank our speaker. Thank you.
Thank you very much, Lily. And I'll be happy to hear from anyone else that might want to ask your questions. Thank you very much.
Okay, so you can send email directly to the speakers, I guess.
Sure.
Thank you. Bye-bye.
Thank you.